A Roman soldier stationed in Germania scratches 3 horizontal lines into a wooden post. A Chinese mathematician in the Han Dynasty arranges counting rods into a triangular pattern. A Mayan astronomer carves a dot above 2 horizontal bars into limestone. 3 different civilizations, 3 different symbols, all representing the same concept that would eventually reshape how humans think about reality itself. But they weren't just counting, they were unlocking the hidden architecture of the universe. 1 represents unity, 2 represents duality, but 3 breaks the pattern entirely. You can draw a line with 2 points, but 3 points give you something completely new. A triangle, a shape that encloses space. 3 transforms counting into geometry. From the moment early humans developed counting systems beyond basic enumeration, 3 became essential to geometry, influential in storytelling, and crucial to understanding everything from atomic structure to musical harmony. Why do we find 3-act plays satisfying? Why do we organize information in groups of 3? Why does a triangle feel more stable than a line? The answer isn't just mathematical, it's cognitive, physical, even cosmic. The symbol we use for 3 today, that curved character that looks almost like a sideways letter M, has traveled through more transformations than any other numeral. In ancient Brahmi script around 300 BCE, 3 appeared as 3 horizontal lines, exactly as you might expect. But watch what happens as this symbol migrated westward through trade routes and conquests. The Gupta mathematicians of 4th century India began connecting these lines, creating a flowing curve that would eventually become our modern 3. When Islamic scholars like al-Khwarizmi encountered this symbol in the 9th century, they refined it further, adding the distinctive curves that made rapid calculation possible. The symbol had to be quick to write. Merchants and mathematicians were doing calculations by hand, and every stroke mattered. Here's what's fascinating. This evolution from 3 lines to a single curve mirrors a deeper shift in mathematical thinking. Ancient counting systems often stopped at 3 because 3 represents the minimum number needed to create spatial relationships. You can't form a triangle with fewer than 3 points. You can't create a stable structure with fewer than 3 supports. 3 isn't just the first odd prime number, it's the first number that creates dimensionality. The Pythagoreans understood this. They called 3 the first true number because it was the first to have a beginning, middle, and end. But their insight went deeper. 3 is the only number equal to the sum of all positive integers less than itself. 1 plus 2 equals 3. This property makes 3 mathematically unique. It's simultaneously a building block and a completion. Ancient civilizations recognized 3's special status in ways that still echo through our culture. The Egyptians organized their pantheon around triads, groups of 3 deities that represented cosmic balance. Later, philosophers developed dialectical thinking around 3-part structures: thesis, antithesis, and synthesis. They weren't being mystical. 3 represents the minimum complexity needed for stable systems. Take the triangle. A line can be bent, a square can be collapsed, but a triangle maintains its shape under pressure. Ancient architects used triangular supports. Modern engineers still rely on triangular trusses. Geodesic domes distribute weight through triangular patterns. The triangle isn't just a shape, it's a solution to the fundamental problem of creating stability in an unstable world. 3's mathematical significance becomes truly extraordinary when we examine its role in prime number theory. 3 is the only prime number that's 1 less than a perfect square, 4, and it's the only prime that's 1 more than a power of 2, 2 squared minus 1. This dual relationship with powers of 2 creates mathematical harmonies that resonate throughout number theory. Now, something genuinely strange, 3 appears to be hardwired into human cognition in ways that other numbers aren't. Cognitive scientists have discovered that humans can instantly recognize quantities of 1, 2, or 3 without counting, a phenomenon called subitizing. Beyond 3, we have to count or estimate. This suggests that 3 represents a cognitive boundary, the limit of what our brains can process as a unified pattern. This cognitive specialness of three explains why we organize information in threes. The rule of three in writing isn't arbitrary. It reflects how our brains naturally chunk and remember information. Life, liberty, and the pursuit of happiness. Government of the people, by the people, for the people. I came, I saw, I conquered. These phrases work because three creates a rhythm that our minds find satisfying and memorable. Three's influence extends far beyond human psychology. In physics, three spatial dimensions define our reality. String theory requires exactly 3 dimensions of space for matter to exist as we know it. The 3 fundamental forces that govern atomic structure, strong nuclear, electromagnetic, and weak nuclear, create the stable patterns that allow atoms to form molecules, molecules to form compounds, and compounds to form life itself. The number 3 also governs the structure of time in ways that aren't immediately obvious. Past, present, and future aren't just convenient divisions, they represent the minimum temporal framework needed for causality. You need at least 3 moments to establish a sequence, a before, a during, and an after. This is why narratives naturally fall into 3 acts: setup, confrontation, and resolution. The 3-act structure isn't a literary convention, it's a reflection of how causality actually works. Even more remarkably, 3 appears in the fundamental constants of mathematics in ways that suggest deep underlying patterns. The Basel problem, solved by Euler in 1734, revealed that the sum of the reciprocals of all perfect squares equals Pu6, and that 6 is 2x3. The Gaussian integral, fundamental to probability theory, involves p and the square root of p, both connected to 3 through geometric relationships. The true depth of 3's significance becomes apparent when we examine its role in what mathematicians call 3-body problems. 2 objects interacting gravitationally create predictable, elegant orbits. Add a 3rd body, you get chaos, literally. The 3-body problem, first articulated by Henri Poincaré in 1887, demonstrated that 3 interacting objects can produce behavior so complex it's fundamentally unpredictable. This discovery shattered the Newtonian dream of a clockwork universe. If you can't predict the motion of 3 gravitating bodies, how can you predict anything in a universe filled with trillions of objects? The answer led to chaos theory, fractal geometry, and our modern understanding that complexity emerges from simple rules when you have at least 3 interacting elements. But here's the paradox. While 3 creates unpredictability in physics, it creates stability in human systems. 3-person groups are more stable than pairs because they can't deadlock. There's always a majority. 3-branch governments resist tyranny through checks and balances. 3-generation families create cultural continuity. 3 seems to be the minimum number needed for robust, self-correcting systems. This duality, 3 as creator of both chaos and stability, points to something profound about the nature of reality itself. 3 represents the threshold between simple and complex systems. Below 3, behavior is predictable but fragile. Above 3, behavior becomes complex but robust. 3 sits at the boundary, the mathematical edge where order meets chaos. Modern mathematics has revealed that 3 governs pattern formation throughout nature. Cellular automata, simple computational systems that generate complex patterns, often require exactly 3 states to produce interesting behavior. The most famous, Conway's Game of Life, uses rules based on neighborhoods of 3 to generate patterns of stunning complexity from simple initial conditions. Even in pure mathematics, 3 continues to surprise us. The recently proved ABC conjecture, if true, would reveal deep connections between addition and multiplication that center on relationships involving 3 numbers. The Collat's conjecture, one of mathematics' most famous unsolved problems, asks whether repeatedly applying a simple rule involving division by 2 and multiplication by 3 will eventually reach one from any starting number. 3's mathematical properties suggest it might be more than just another number. It might be a fundamental organizing principle of reality itself. From the three-dimensional structure of space to the three-generation genetic memory that shapes evolution, from the three-act structure of stories to the three-body problems that create chaos, three appears wherever complexity emerges from simplicity. The Roman soldiers' three scratches in the wood, the Chinese mathematicians' triangular arrangement, the Mayan astronomers' carved symbols, they were all touching something deeper than mere counting. They were encountering the mathematical structure that underlies pattern, meaning, and complexity itself. 3 isn't just the first odd prime or the sum of 1 and 2. It's the number that transforms counting into geometry, sequence into story, and simplicity into the beautiful complexity of the world we inhabit. In learning to count to 3, humanity didn't just gain a tool for commerce or measurement. We discovered the key to understanding how the universe builds meaning from chaos, one triangle at a time.